This diagram illustrates the electromagnetic spectrum. Notice this narrow band between 400 and 750 nanometers. This specific frequency range is what we detect as visible light. Because these wavelengths are measured in billionths of a meter, they are infinitesimally small compared to the objects we interact with daily. At the macroscopic scale, the wave-like undulations of light become negligible. To study how light interacts with lenses and mirrors, we use the rectilinear approximation. We model the light as traveling in a continuous, perfectly straight line. We call this simplified linear path a ray. By abstracting the complex quantum mechanics of electromagnetic waves into these simple geometric rays, we can predict optical behavior using pure, scalable geometry. Geometric optics takes these physical light rays and maps them directly onto mathematical coordinate systems. This algebraic mapping acts as an engine, allowing us to calculate focal ranges across any distance. The equations we use to engineer massive astronomical telescopes, capturing light from objects millions of miles away, are the exact same mathematical rules we use to make microscopic adjustments to the curvature of the human eye. To master the design and function of any optical instrument, you must first master the Cartesian algebra that predicts how it bends light. We begin by establishing the absolute center of the system. The optical pole of our mirror or lens is placed exactly at the origin, coordinate 0, 0, of a standard Cartesian plane. The system relies on one unbreakable rule. Incident light must always be calculated as traveling from left to right. Any distance measured against the flow of incident light, moving to the left of the origin, falls into the negative domain. We denote the distance to the object with the variable u. Conversely, any distance measured in the same direction as the light's flow, to the right of the origin, is positive. Three core variables live on this grid: u for object distance, v for image distance, and f for focal length. The positive or negative mathematical sign attached to these variables dictates whether an image physically exists in space as a real image or if it is merely a virtual projection. This algebraic equation is the general lens formula. 1 over v minus 1 over u equals 1 over f. This maps the exact relationship between the object, the image, and the focal length. Let's apply specific parameters. We place an object at u equals negative 14 centimeters, facing a concave lens with a focal length f of negative 21 centimeters. To find out exactly where the image will form, we isolate the unknown variable, v, using standard algebra. The calculation yields a v of exactly negative 8.4 centimeters. Translating this mathematical output back into physical reality, we know the image forms 8.4 centimeters to the left of the lens. Because v is a negative number, the math proves the resulting image is virtual, erect, and diminished. We have accurately predicted the physical properties of the system before manufacturing a single piece of glass. This predictive power scales up through coaxial placement, where multiple thin lenses are aligned sequentially along the same principal axis. To find the total optical power of the system, we use a simple combination formula. 1 over the total focal length f equals 1 over f1 plus 1 over f2. The critical mechanism here is the handoff. The calculated image distance, v1, produced by the first lens becomes the literal object distance input, u2, for the second lens. Complex optical instruments do not require new physics. They are simply iterative mathematical loops applying the single lens formula over and over. Consider an astronomical telescope in normal adjustment. The objective lens captures parallel incoming rays originating from optical infinity. In this specific telescope, the objective has a focal length of 144 centimeters. These incoming rays converge at that exact focal point, forming a real intermediate base image. This completes the first step of our sequential loop. An eyepiece lens is placed 6 centimeters away, designed solely to act as a simple magnifier analyzing that intermediate image. For a telescope in normal adjustment, the angular magnification is calculated by taking the ratio of these two focal lengths, FO divided by FE. Dividing the objective's 144 centimeters by the eyepiece's 6 centimeters gives us a total magnification of 24. Geometrically, to achieve high magnification, the math dictates a strict requirement. Maximize the focal length of the objective lens and minimize the focal length of the eyepiece. This precise algebraic logic extends directly to biology. The human eye is an advanced compound optical system. We can map the eye directly onto the Cartesian plane, anchoring the cornea and eye lens at the exact mathematical origin point. The baseline converging power of the human eye comes from two components. The cornea provides roughly 40 diopters of power, and the eye lens fine-tunes the focus with an additional 20 diopters. Our target is to form a sharp image exactly on the retina, located on the positive x-axis. Myopia, or short-sightedness, is a geometric failure. Incoming parallel rays converge too early, creating a focal point before reaching the retina. Physically, this happens because the combined converging power of the eye is too strong, or the eyeball has elongated beyond the required focal length. Biological vision failure is an algebraic mismatch between the system's focal length and the retina's physical position on the coordinate grid. Correcting myopia requires a mathematical fix. We must introduce negative optical power into the biological system. We achieve this by placing a diverging concave lens directly in front of the optical origin. Adding a negative 1.0 diopter alters the input vectors. Incoming rays diverge slightly before entering the eye, pushing the final convergence point backward onto the target retinal line. The scale of these calculations is vast. We use the same equations to aim a 144-centimeter telescope objective at the moon, as we do to place a negative 1.0 diopter corrective lens on a human face. The Cartesian sign convention accurately predicts the outcome in both scenarios. From the macroscopic reaches of astronomy to the microscopic adjustments of human biology, our ability to understand optical systems relies entirely on mapping the rectilinear propagation of light onto rigid algebraic geometry.